All right, let's dive into a bit of a cosmic detective story. The main clue? Well, it's something we see all the time, but we don't really see it, and that's the light from distant stars. You know, those tiny little rays are basically messengers, carrying secret codes about the very fabric of the universe. So let's start cracking them. I mean, we all know what a rainbow is, right? That beautiful arc of color you see when sunlight hits raindrops just right. It's one of those things we've all seen. But what we're seeing is really just the first clue.
Because that simple, everyday rainbow, it's just the very beginning. Think of it as the first page in a huge cosmic story. And this story is written in the language of light itself. And if we can learn to read that language, we can figure out what stars are made of, even from millions of light years away.
So to crack this cosmic code, we've got to look way beyond the rainbow. It turns out those beautiful colors our eyes can see are just a tiny, tiny fraction of the whole story that light has to tell.
We've got red, orange, yellow, green, blue, and violet. Roy G. Biv, right? This is our visible spectrum. It's the full range of light our eyes evolved to see. But what if I told you that only seeing these colors is like hearing just a single note from a giant cosmic piano?
Well, here's the whole piano. This is the entire electromagnetic spectrum. And that familiar rainbow we all know, it's just that tiny sliver in the middle we call visible light. Everything else, from these long stretched-out radio waves all the way to powerful, zippy gamma rays, it's completely invisible to us. So what's the difference between all these types of light? It really comes down to something called wavelength. Just think of light as a wave. Over on the left, you've got radio waves, and they're really stretched out. They have very long wavelengths. And on the right, you have gamma rays, which are super compressed, with incredibly short, tight wavelengths.
And wavelength has this inverse relationship with frequency. It's really simple. A long wavelength, like a radio wave, means fewer waves are passing by a certain point every second. That's low frequency. A short wavelength, like an X-ray, means a ton of waves are zipping by every single second. That's high frequency. They're basically perfect opposites.
And here's the real kicker, the most crucial point. The higher the frequency, the higher the energy. Those low-frequency radio waves, they carry very little energy. But the high-frequency gamma rays, they are packed with an enormous amount of it. This link between frequency and energy is really the fundamental thing that separates all the different kinds of light.
Okay, so now that we know about this whole invisible spectrum, how do astronomers actually use it to read starlight? Well, they do it by looking at a star's spectrum, which is basically its light spread out like a rainbow. And it turns out these spectra come in three very distinct types.
First up, you've got the continuous spectrum. This is what you get from something that's really hot and dense, like the core of a star. It's just a perfect, complete, unbroken rainbow, with all the colors blending smoothly one into the next.
Second, you have the emission spectrum. Now this is totally different. Imagine a hot, thin cloud of gas. Instead of giving off a full rainbow, it only emits light at very specific colors. This creates a pattern of bright, sharp lines. And here's the cool part. That pattern acts like a unique barcode for whatever element is in that gas.
And third, there's the absorption spectrum. This is what happens when light from a hot source, like that star core, passes through a cooler cloud of gas. That cool gas cloud literally absorbs light at the exact same specific colors it would emit if it were hot. So the result is a rainbow, but with dark lines missing. It's like a barcode in reverse.
So these lines, these barcodes of bright or missing light, they're the key to everything. But to really get it, we have to go from the massive scale of stars all the way down, way down, to the level of a single atom.
So where does light actually come from? What's making it? The answer has to do with those tiny little electrons that are always orbiting the nucleus of every single atom. They are the light makers of the universe. So let's start with absorption. Picture an electron in a nice, stable, low-energy orbit around an atom. Now, if a particle of light, a photon, with the exact right amount of energy comes along and hits it, that electron absorbs the photon. This jolt of energy makes it leap up to a higher, more energetic orbit. And that photon it just swallowed, that's now a missing piece of light. And that's what creates those dark absorption lines we saw.
But that high-energy state, it's unstable. The electron doesn't want to be there. It wants to get back to its comfortable, low-energy home. To do that, it's got to get rid of that extra energy it absorbed, so it falls back down. And as it does, it releases that energy by spitting out a photon of light with a very specific color and energy. And that right there, is the birth of light. That's the source of those bright emission lines.
So now we can put it all together. We can connect that tiny little electron leap inside one atom to figuring out the chemistry of a massive distant star. This is where our cosmic detective work really pays off.
And this is the fundamental truth that makes all of this possible. Just like every single person has a unique fingerprint, every single element in the universe, we're talking hydrogen, helium, carbon, iron, you name it, has its own unique spectral fingerprint, its own unique barcode of light that it absorbs and emits. No two are the same.
So, by capturing the light from a star millions of light years away and spreading it out into a spectrum, astronomers can literally read these barcodes. They can see which dark lines are there in its absorption spectrum and match them to the known fingerprints of different elements. This lets them figure out exactly what a star is made of, and even how hot it is. It's absolutely incredible when you think about it.
So let's just take a step back and think about what we've just uncovered. We've gone from the familiar colors of a simple rainbow to the huge, invisible world of the electromagnetic spectrum, and then zoomed all the way down to the quantum leap of a single electron.
If there's one thing to take away from all this, it's this. Light is not empty. Every single photon zipping across the vast emptiness of space is a tiny little messenger, and it's carrying detailed information about exactly where it came from, whether that was a star, a gas cloud, or a galaxy billions of light years away. And these messengers, they travel at the ultimate cosmic speed limit, the speed of light. That's 300 million meters per second. To put that in perspective, that's fast enough to go around the entire Earth more than 7 times in a single second. And for thousands or even millions of years, these photons travel, carrying their secrets until they finally end their journey in our telescopes. And that leaves us with one last, kind of mind-blowing thought. By learning to read this amazing language of light, we've figured out the chemistry of the entire cosmos. But if every single ray of light is a message, you have to wonder, what else is the universe trying to tell us that we just haven't learned how to translate yet?